I'm now going to show you one more network, and it is actually, this model is quite interesting in itself. I would say quite a different idea, slightly similar to what Lohit was trying to do. I'm going to put it in a more standardized way over here. So you see our same network. I'm just uh, making change in IOSH's code. Let me do this here. I'm just running these cells again. So I'm just a graph with 0 nodes and 0 vertices. And let me just have 10 vertices as of now. So if you look at the summary of this graph, it has 10 vertices. Let me just remove this for some time. And what I'm going to do now is, rather than creating some edges randomly, my first idea will be to create triangles in a graph. So similar thing, first create triangles and then add randomness on top of it. This model came in 1998. Two scientists called Watts and Strogatz gave this model. After this, we have one more model, which we'll discuss in the Wednesday's class. So let's talk about this one over here. So let me write a code, and can you try to predict what kind of a network will it give you? So I have 10 vertices. Take a look at this. I'll say for I in range 10, G dot add edge from I to I plus 1. What do you think that will do? Right, so let me run this code, and it actually gives me an error. It says I'm trying to add edge on the top of some invalid vertex. Do you see what I'm trying to do here? Trying to connect vertex 0 to 1 and then 1 to 2 and then 2 to 3 and then 3 to 4. Something like a bucket brigade network. I'll make a small change to this. So the problem here is when I reaches 9, I'm trying to add an edge from vertex 9 to vertex 10. But I have no vertex 10. My vertices are numbered from 0 to 9. So to count that, I'll add a modulo 10 here. You should see what that will do. If I do a modulo 10 here, you see it will start right from the beginning. So this becomes 10 modulo 10, which comes back to 0. Just think about it. And let me just like we did previously, let me get all this code here just to be safe. And after adding all these edges, I would like to plot this graph and see how it looks. So this is what we get. So I can actually add one more argument here and ensure that we could see a smaller graph. Let me make it 250 cross 250. I think that should be fine. Right, so you see this kind of a circle here. Well, not exactly a bucket brigade network. We ended up making a ring. So take a look at this code and try to understand it. And this is the beginning of the model. You'll say, what is this? This is definitely not at all like a real world network. What are we trying to do? So if you look at this network, what do you think its density will be? Because its density is definitely going to be low. You have n nodes and n edges. Out of n choose 2, you only have n edges. You have a low density. Talk about transitivity. There are no triangles at all. Transitivity is 0. So let's look forward and see if we can include some transitivity in this network. I want to introduce some triangles, and that's where the model picks up. You see what I'm going to do? I'm going to add an edge from I to I plus 1 modulo 10. Rather, let me make it slightly different. Okay, let me add one more edge. I'm going to make a small change here. I'll take I from, let's say, 1 to 11, right? So it goes from 1 to 10. So you see for each vertex, I'm starting from 1, 2, 3, 4, 5, 6, 7, 8, and there is no 10 here. How can I do it? So let me do it this way. 1 to 11 modulo 10. that will bring me from 1, 2, 3, 4. 11 modulo 10 is again going to be 1. I basically want to go all the way from 1 to 0. Okay, let me keep it this way. So let's say 10 only for I in range 10. So you go from 0 to 9. And let's say every time I add an edge from I to I plus 1 modulo 10. And let's say I to I plus 2 modulo 10. I think this is easiest to understand. So you see what I'm trying to do. I'm not only connecting 0 to 1, I'm also connecting 0 to 2. Right? And then I'm not connecting 1 to only 2, I'm also connecting 1 to 3, so on and so forth. So let me just run this, and this is the kind of network you end up getting. Do you see what is happening here for each node? So if you look at each node, it is connected to one on its left, one on its right, in clockwise and anti-clockwise direction, and then to one more. And mostly this was the model. This is the second model, which is all about, you see, we have incorporated so many triangles here. And I have a question for you here. What do you think is the transitivity of this network? So you see many open triads here. Do you see 4, 6, 8? It's an open triad. 5, 3, 2. It's an open triad. 4, 3, 5, 3, 4, 5. That's a closed triad. The question for you, what fraction of triads do you think are closed here? Can you give me a mathematical proof? Again, you can pause your video and put the answer in comments. It's very likely that all these questions that I'm asking you in these videos, you'll see them in exams also. Just hope you'll take them seriously, and if you are unable to solve them, we can discuss them in the next class. So anyways, this is the network we got. This is the model we got. Let's do it for more number of vertices. So we had 121 nodes. So everywhere, let me change this 10 to 121. And then let's look at the properties of this network. And this doesn't look very nice. I should basically do something with its layout over here. So I don't want this kind of a layout. Let me see if I can get it to a circular layout. I don't remember how to do that. So let me ask. Python iGraph circular layout. I've done that on ChatGPT, but I think it's fine. And this is iGraph R. I want that. iGraph, Python layout, Python iGraph. Let me see if I can find circle in here. It is difficult to find your answer here. You can fast forward this part of my video. Python iGraph, plotting, layout, graph plotting. Okay, let's see. Layout equals to, I want a circular layout, graph dot layout underscore circle, and how to use that. Let's just try something and hope it works. Let me use this and see if I'm going to work. Layout equals to g dot layout, layout equals to circle, and then I need to include that layout in there. I think it's automatically included. You don't need to add anything in here. Doesn't work. Okay. What if I could just decrease vertex size to 2. I'm getting this weird looking graph here. Let me remove labels for some time. Okay, so I think this is still better. I need to check out how to get it in circular layout. If you could do that, maybe you could just help us in the comments. So this is the kind of a graph you get. It looks like a bracelet, but you see somehow I'm unable to see triangles here. Let me just remove this also and check if we could see the triangles. You see now a little bit you could see the triangles over here. It was easy to visualize it for a small graph, but you see as soon as we start visualizing larger graphs, it starts going out of our hand and we need more layout based algorithms. But you see if you would zoom in, I hope you can see a few edges here. You could see a few triangles here. If I could slightly reduce it, let's say, and I think that's fine. If I could zoom it in, you could see some triangles here. Okay. Anyways, so we have quite a lot of triangles here. And then, but the question remains is that how many? Anyways, we'll figure that out. You should tell me how much transitivity we get. I'm not going to answer here, but I can tell you we'll get a good deal of transitivity here. Right? This is a network that we have, but it doesn't still look very real worldly. You see what is missing over here. Let's again talk about three most important graph properties that we were talking about. G dot density. Well, yes, I have a low density. It's just close to 3%. And then transitivity, I'm not going to show that to you. I want you to figure that out. And before writing a program for it, think mathematically. What do you think is the transitivity for this network? Another thing I'm interested in looking at is average path length. You see, your average path length was very small. It was only 4 for our original graph. But if you look at average path length, it is 15. So it's not a small world. If you want to go from any vertex to any other vertex, you'll need to go to almost 15 hops. So you see, that is something that we want to reduce. We got some properties of a real world network. We got a giant component here. We can just add a few little bit of nodes here and there to make multiple components. That's not a big deal. And then we also got good amount, a small density over here. And what we want to do now is to reduce this average path length. How do we do that? That is the final step to this model. So if you remember, we said first you make some triangles. We have made a whole lot of triangles. And now we just want to add some random edges on top of it. And once you do that, you see your average path length will reduce. But I'm interested in seeing how many random edges should I add here so that this average path length reduces. So in order to do that, in order to show you how many random edges should be added, I'll take all the more a bigger graph. And that bigger graph will be a replica of this graph only, but just with more nodes. Let me actually create a network on 4,000 nodes with a lot of triangles. And what I'm interested in, I want to look at when I add some random edges, how does the average path length reduce? So let me first create this network on 4,000 nodes. It is done. Let's look at the average path length. It is 16.8. I want to reduce it. If it was a Facebook graph, I would want average path length to be somewhere around 4. What I'm going to do next is let's add a random edge here. I'm going to import random. I guess that's already imported, but it's fine. I'll choose to vertex g equals to random.randint. Give me a vertex from range 0 to 3,999. Right? That's my last index. So you should remember that when you use this random.randint, both of these indices, they are also included. So you get two random nodes over here, and then you add an edge here from U to V. Once you have done that, again tell me the average path length. Right? So you see, it comes down to 14. Let me run this code again. Comes down to 13, comes down to 11. Now, I really don't know whether this decrease, it is linear or exponential. It seems like it is reducing really slowly here, really slowly. So instead of running this code again and again, let's plot it on a graph and then see how this average path length reduces. I'll run this code again and I'm going to create a list. What it's going to do is, let's say for I in range 100. So 100 times I'm going to run this code. I'm going to choose two random nodes, add an edge between them, and once I have done that, so here also I'm going to append g dot average path length, and every time I add an edge, a random edge to this network, I'll again append to L average path length. I'll do this 100 times and let's see how L looks like. It might take some time. It would have been better to print I also. Didn't expect it to take so long. Okay. Can you guess why this code took so long to run? It's taking long to run because finding this average path length, this part of the code is what is taking time. Every time you're trying to find shortest distance between all possible pairs of nodes. So there's the shortest path algorithm running in the background. And this is how my average path length is decreasing. If we can just plot it, and that will give a better idea of how it's changing. So if you don't have matplotlib, you might want to just install it. So you see, although this looks linear, this decrease in your average path length is exponential. So it comes down from 16 to 8 like really fast, and after that it slows down. So if you have some really big graphs, if you are adding these random edges, your decrease in the average path length, that is exponential. That means you only need to have a few random ties to make this a small world, right? And if you keep on adding random ties, you add a whole lot of them, then even this model, it will become equivalent to your random model. So that's all about this model. I'll just give you a quick recap. The idea is you start with a ring-like structure, right? And not exactly a ring-like structure. You connect every node to two nodes on its left and two nodes in its right. That gives you sufficient triangles, gives you sufficient clustering. And after that, you just add some random edges on top of it, right? So if I run this code, and you see I added 100 random ties here. In 100 random ties, the average path length decreased from 16 to 6. That's what makes this network a small world. So for a quick recap, the properties of real-world networks that we are working till now, they are only giant component density, they are small world, small average path length, and a high transitivity. In the next lecture, we'll see an altogether different property, which is, I guess, one of the most important and interesting properties till now. We have completed two models today. We'll complete last model in the next class, and then we'll move on to other topics.